So far we have been exploring PageRank, and we have formulated it as this eigenvalue problem, and we added the random walks and teleportations to it. So now what we will look next is actually how do we really compute PageRank for the web scale graphs. Basically, how do we compute it for graphs that don't even fit into the main memory of a machine. So let's look at what we know so far. Right? What we know so far is that the key step in computing PageRank is this vector matrix multiplication, where we are computing the new vector R by taking the matrix M and multiplying it with the old vector R. Right? This is very easy to do if we have enough main memory in the machine to store both A, the old version of R, and the new version of R. Now, let's look at what is the structure of matrix A, and we will notice one thing that is kind of striking. Right, so here I have an example from our previous slide with the three node graph, where our matrix A equals the matrix M times beta plus 1 minus beta times this matrix of 1 over n's, where n is the size of the graph, and the size of this matrix is m by n. Right, so notice down here what happens, right? We take our matrix M, multiply it with 0.8. We take this matrix of n by n, where every entry is 1 over n, multiply that with 0.2, and sum these two matrices together. So what happens now is that our matrix A is this big matrix with non-negative entries, and what we notice is that every entry in this matrix is non-zero. So initially our matrix M had a number of zeros, but now our matrix A has no non-zeros. So what is important now is that the amount of memory we will need to store A will be actually huge, right? A is now what is called a dense matrix. Let me just give you an example. So imagine we have a graph on 1 billion nodes. So basically we have 1 billion web pages. And 1 billion web pages is a very tiny fraction of the web graph. So this is a small graph from the web size point of view. And let's assume that we need, let's say, 4 bytes to save each entry of this graph, right? So to save a node ID. So this means that, for example, to store 1 billion pages and edges, this means that we will need around 2 billion entries, and this means that we will need around 8 gigabytes of memory to store matrix M, for example. But for example, if we would have to want to store all the entries of matrix A, now the size of the matrix A is n by n, which is n squared, which means that we would have to store n squared entries. And the amount of memory we would need would be like 10 to 18, which is a huge number, and we would never be able to store this in memory. I think there is not even, if we take all the computers in the world, they don't have enough memory to store 10 to the 18 bytes or integers in memory. So the question is, what can we do? Is there a way to get around this and kind of preserve the sparsity of the matrix M, right? Basically, the idea is that in real matrices M will be extremely sparse, meaning that an average page only points to 10 other pages in the graph, right? So this means that rather than storing the whole vector of zeros and then only a few non-zero elements, we kind of only want to store non-zero elements. So here is basically the idea, and how we now can solve the PageRank problem. So just to remind you, we have the capital N number of pages or number of nodes in the graph. We are now we defined matrix M that's in such a way that the entry Mij is 1 over the degree of j if node j points to node I, and otherwise that entry is 0. And now let's think about how do random teleports play with this into this matrix M, right? So basically the way we can think of teleports is basically we take our initial graph and add all these additional transition edges, right? So we can think that random teleports basically take our graph and transform it into a completely connected graph where we have two types of edges. We have the edges that correspond to the hyperlinks, and then we have the edges that correspond to random teleportations, right? Whenever we can teleport from one node to another, we add an edge, and we say that kind of a random surfer traverses this edge with a very small probability. And this is exactly what we will do now, right? So basically adding a teleport link from node J to every other page in the graph, and we want to set this teleportation probability of such teleport link to be 1 minus beta, right? That's the probability of a teleport times 1 over n. right? This is the number of web pages, so that's the probability of traversing one individual teleportation link, right? This also means that what we need to do is now that on all the other links of the web graph, we have to reduce their transition probabilities, right? So the transition probabilities go from 1 over the out degree of node j to beta times 1 over the out degree of node j, right? So now basically what we did is we took our graph and we in some sense transformed it into this fully connected graph with different transition probabilities over the edges that correspond to the hyperlinks and edges that correspond to teleports. However, what we notice is that this transformation is actually equivalent to saying that we will tax the PageRank of every page by a fraction of 1 minus beta, and then we will take this 1 minus beta fraction of the PageRank scores and we will distribute them evenly, right? Meaning that this random teleportation part of the PageRank score gets evenly distributed among the web pages. So this is the intuition. So let me now show you how the mathematics works out. We will start again by looking at our initial PageRank equation, R equals A times R, where the way we define M, just to remind you, is to take every entry ij of matrix I is simply beta times the corresponding entry of matrix M plus 1 minus beta over n, where n is the size of the graph, right? The way we think about this is basically to say the transition of a random walker from node j to node I is simply the beta times the transition due to the random walk plus a small constant factor that happens due to a random jump probability transition, right? So now that we have this, let's unpack our PageRank equation. If we unpack this PageRank equation, basically what we are saying is that entry I of the rank vector R is simply a summation over the j's, where j range from 1 to n, aij times rj, right? What we will do now is we will take this a and expand it into the equation we have above. So if we do this, what we notice is the following, right? This is still simply a summation. Here I'm expanding the definition of A now into how we computed matrix A, and I have my entry from the rank vector R. So now I can distribute the summation, and here is what happens, right? So we have now two summations, both over the same range, and what we observe now is one thing that we know is that vector R is a probability distribution, which means that the entries of vector R sum to 1, which means that this second summation here, the entries, the sum over j of rij sums to 1. So the second summation basically simplifies to just this constant of 1 minus beta over n. So notice what we did right now. What we did is basically we expressed our R equals A times R into a different expression where we say that R equals beta times M times R plus some constant, right? What this means is now basically that we never really need to explicitly express matrix A, right? We never really need to materialize this big, dense matrix where every entry is non-zero. We can only work with matrix M because matrix M is full of 0 elements which we don't need to explicitly store, so we can actually work with much smaller matrix. So this is basically the good thing that happened here. So rather than working with a big n squared size matrix, we are now working with a very small matrix. And let me just demonstrate how much difference this makes in practice, right? So what we did in the few last slides is basically we rearranged our PageRank equation into a different equation that doesn't depend on A, but only depends on our matrix M. Right? So now what is important is that matrix M is sparse, right? What do I mean by that is, for example, in the matrix M, if you think of it as a matrix in every row, even though this matrix is, let's say, 1 billion times 1 billion, like 10 to the 9 times 10 to the 9, the number of non-zero entries in every row on average will be around 10. What this means is that an average page has around, let's say, 10 outlinks or even 100 outlinks. But the point being is that out of 1 billion entries in every row of this matrix, there will be only 100 non-zeros. So this means that rather than storing the full n squared number of cells in this matrix, we will only store the cells that actually have the non-zero value. So what this means is that in every iteration of our PageRank equation, basically all we need to compute in some sense is the product of our matrix M with our old rank vector, and then add a constant value to every rank score just because of the random jumps. Of course, here I was assuming that our graph M has no dead ends. If our graph will have dead ends, this means the vector R won't sum to 1. So after everything is done, we will have to kind of expand it back to normalize to 1. I'll talk about this a bit more in the next few slides. So here is now the complete algorithm for PageRank, how one would go and actually implement it in practice. So the way this works is, on our input, we are given a directed graph G, and we are given a parameter beta. This is the teleportation parameter beta, right? And what we are assuming in this algorithm is that our graph has both spider traps and dead ends. Kind of nothing will break. The algorithm is robust regardless of whether these dead ends and spider traps actually happen. So the output of our algorithm is now a PageRank vector R, and the way the algorithm operates is the following. At the beginning, we set all the PageRank scores to be 1 over n, to be equal, and we set time equals 1. And then we have this loop where we iterate until our PageRank vectors will converge, which means that the PageRank vector between time step t minus 1 and time step t, the individual entries do not change much, but do not change more than some small value epsilon, and this epsilon is again a user set parameter, something small, but and depending on how small this value is, this is the number of iterations the algorithm will need to converge. Okay, so now we explained the outer loop. So now let's look what happens in the inner loop. So in the inner loop, first we have another a for loop where basically we go and update the PageRank score of every node by simply taking the PageRank scores of every node I that points to it, and then divide that by our degree of I. This is the first part. Of course, here we have to be careful if node j has gets the rank 0, if the in degree of it is 0, right? So if a node has no in degree, then we set its PageRank score to 0. And then, of course, what happens now is that if we have dead ends, the PageRank will leak out. So now we need to figure out how much of the PageRank has leaked out, and then reinsert the PageRank, the missing PageRank scores into our rank vector. So what we do here is the following. We compute what is the sum of the components of our PageRank vector R so far. We call this S. We want this S will be less than 1. So what means is that 1 minus S amount of PageRank has kind of leaked out. So we want to now take this and evenly insert it to every entry of R. So this is exactly what we do. We say, now we go over vector R again. We say the true value of the PageRank score is whatever we had before, plus this missing part of the PageRank score, right? 1 minus S over n, which means that every node n gets 1 minus S times 1 over n fraction of the leaked out score, so that now again our vector R will sum to 1. So with this, basically we obtained the new version of R. We check for convergence, and we keep repeating until we converge.